continue where we left in the previous lecture. We were discussing Navier-Stokes equations, that is we discussed part of constitutive relations for a Newtonian fluid. That is where we left in the previous lectures. We are going to continue from there and complete Navier-Stokes equations and energy equation in this lecture. So, a summary of what we discussed in the previous lecture: we derived the Cauchy equation using a differential control volume, and then we started off with constitutive relations for different types of fluids, and in this lecture we would focus primarily on Navier-Stokes equations for Newtonian fluids and energy equations. Outline of this lecture: we will complete the constitutive relation for a Newtonian fluid, and then we would substitute this in Cauchy equation to obtain the celebrated Navier-Stokes equations. We will have a look at few simplified forms. Euler equation is one of the most prominent amongst them, and then we would move on to the derivation of energy equation for a fluid body. So, this is where we were, that we wanted to find out a constitutive relation for a Newtonian fluid for which the stress and strain rate relationship is linear, which is given by tau is equal to minus pi lambda plus divergence of Vi plus twice of mu s, where s is our strain rate tensor. How do we obtain this equation? This is what we would discuss in bit more detail. Now, let us have a look at the constitutive relation for a Newtonian fluid. Now, in the case of Newtonian fluid, we say that the stress tensor must be linearly related to strain rate tensor. So, the most general form of this relationship of a linear relationship can be written as tau ij is equal to Aij plus Bij. Now, I have broken it in two parts. So, here Aij, this part does not depend on velocity. So, it basically corresponds to the stresses at rest, that is the stress at a fluid in a state of rest, and Bij, this is dependent on fluid motion. Basically, it would be proportional to the gradient of velocity, or more particularly it is proportional to strain rate tensor. So, if you recall, at the end of the previous lecture we talked about the stresses in a fluid at rest. So, if you look at that particular case, what we call case 1 is fluid at rest, and you can easily identify that our Aij is basically minus p times delta Ij, where delta Ij is Kronecker delta, which is a second order isotropic tensor, and P is our thermodynamic pressure. Thermodynamic pressure which is related to thermodynamic state of the fluid. For example, P is equal to rho RT for an ideal gas. Now, when we are dealing with fluid motion, we have a case 2. Fluid motion, that additional stress term Bij is generated due to viscous action. Now, this additional term Bij, we commonly refer to it as deviatoric stress tensor, and we use the symbol sigma ij for it. Now, this component is proportional to velocity gradients. In fact, we can easily show that the sigma ij depends on the symmetric part of gradient of velocity, because the antisymmetric part which represents the rotations, they do not contribute to stress generation. Hence, we can express sigma ij as a product of a fourth order tensor, let us call it as K Mn multiplied by Emn, where Emn is our strain rate tensor. Now, as far as tensor K is concerned, in general it would have 81 components, which basically represent or depend on the thermodynamic state of the fluid. But this should satisfy a specific requirements. For instance, this stress strain relationship must be independent of rotation of the coordinates. So, stress strain relation must be independent of a rotation of coordinate axis. And this requirement implies that Kij Mn must be an isotropic tensor. So, if that were the case, then we will have a lot fewer components in K. In fact, this K can be expressed as a product of 3 constants and second order isotropic tensor delta ij. So, K I j m n, this is given by lambda times delta ij delta m n plus mu times delta I m delta I n plus gamma times delta I n delta j m. Now, here this we have got 3 constants lambda, mu and gamma. These depend on thermodynamic state. The state of the fluid. We have got yet another requirement, that our Newtonian fluid is isotropic and our stress tensor is symmetric for an isotropic medium. So, stress tensor is symmetric, which requires that this K I j m n must be symmetric with respect to I and j indices, and this is possible only if gamma is equal to mu. So, this requirement reduces the number of material properties which we require by 1. So, now what we are left with is only 2 material properties, that is our K I j m n is equal to lambda times delta I j delta m n plus twice of mu delta I m delta j n. So, now these 2 material constants, they have got a specific name, lambda and mu are historically referred to as coefficients of viscosities. Our task would be to see what happens if we substitute this expression for K I j into sigma I j. So, our stress tensor sigma I j would be given by, so now sigma I j becomes lambda times delta I j delta m n E m n plus twice of mu delta I m delta j n E m n, and this expression simplifies to sigma I j is equal to lambda times delta I j E m m plus twice of mu E I j. Now, we can clearly say that this EMM, it is nothing but divergence of the velocity vector, and Eij is our usual strain rate tensor. So, now we can substitute for sigma ij in expression for tau ij, and our stress tensor tau ij is given by minus p delta ij plus lambda delta ij E m m plus twice of mu E I j. So, this is a generic relationship between the stress tensor and strain rate tensor for a Newtonian fluid. Now, let us see what further simplifications we can have. If our fluid were incompressible, or the fluid flow were incompressible. So, for an incompressible flow, divergence of the velocity vector, which is what this EMM represents, this is equal to 0, and we get a simpler relationship. So, the simplified form for incompressible flows is tau ij is equal to minus p delta ij plus twice of mu E I j. That is, we have got a single material constant which relates the stress tensor to the strain rate tensor, which is our usual coefficient of viscosity. So, mu is fluid viscosity. So, this is what we had, that the expression which we have obtained, tau is equal to minus p I plus lambda times divergence of V into I plus twice of mu into S. And for incompressible Newtonian or Stokesian fluids, we had tau is minus p into I plus twice of mu times S. Can we obtain a similar relationship or simpler relationship for general or compressible Newtonian fluid? That is what our task would be. So, for a general fluid, what was observed by Stokes is for compressible fluids, or rather compressible Newtonian fluids, we have got a term which is called bulk viscosity, which is given by kappa lambda plus 2 by 3 mu, and this was observed by Stokes to be very small. So, the Stokes hypothesis is this kappa is almost equal to 0. This is a measurable quantity, but measurement of kappa would require very large velocity, so very large density gradients which occur only in shock waves, and for majority of engineering fluids, for instance air and water, we have observed this Stokes hypothesis works pretty well. So kappa equal to 0, this implies that our lambda is equal to minus 2 by 3 mu. So with the Stokes hypothesis, now we have got only one material constant or material property which is there in stress strain relationship, and now we can express our stress tensor tau ij as minus p plus 2 by 3 mu divergence of the velocity multiplied by delta ij plus twice of mu e ij. Now since this relationship which we obtained was based on Stokes hypothesis, so this is also called constitutive relation for Stokesian fluid. And if we substitute this expression for tau ij in our Cauchy equation, the resulting equation is referred to as Navier-Stokes equation. So this is what we get if we substitute for tau ij using Stokes hypothesis. We get a general form of Navier-Stokes equation given by del rho v by del t plus divergence of rho vv is equal to rho b minus gradient of p plus twice of divergence of mu times s minus 1 by 3 divergence of v into I. Now this equation was independently derived by French gentleman Navier and the British gentleman Stokes. That's why these equations are referred to as Navier-Stokes equations. We can have various simpler forms or simplified forms of these equations. We have already seen one form for incompressible fluids. And that simple form is given by del over del t of rho vi plus del over del xj of rho vi vj is equal to minus del p over del xi plus twice of mu del over del xj del of vi over del xj plus del of vj over del xi divided by 2. Now if we assume we can if you want we can divide by density on both the sides, but let us leave it as such by noting here that density rho is constant. Now if temperature variations were small, mu can be assumed as a constant and simplified form of this NS equation for an incompressible flow can be given as del V over del T plus divergence of V V is equal to minus gradient of P divided by rho plus nu times Laplacian of V. For Newtonian fluids we can have few other simpler forms, and other simple form is what we call for inviscid fluid, which leads to our so called Euler's equations. Now, this Euler's equation is specifically valid for high speed flows. For example, around an aircraft, okay. Now, away from the solid surfaces, that viscous effects can be neglected or negligible, and hence our stress tensor is just that due to pressure, and we get a very simple form for this equation. Viscous terms drop out, and what we get is del rho V over del T plus divergence of rho V V is equal to rho B minus gradient of P. So, this simplified form was derived by Euler, and this was called Euler's equation, and it is very widely used in numerical flows simulation for flows over aircraft and wing bodies. There is yet another case of interest, which is extreme of that of the Euler equation. Suppose what we had is for low Reynolds number flows. Now, Reynolds number could be low because of what? That flow velocity is very small, or the second case is the fluid is very viscous, or the third condition could be geometric dimensions so very small. This last case could occur if we are dealing with electronic devices or the flow through biological systems. We have got very small length scales in capillaries. So, in such situations, in either of these situations, what we would have is our non-linear convective terms which are represented by this divergence of rho Vv, these are negligible. And the flow is dominated primarily by pressure, body forces and viscous forces. So, such a flow, this particular flow is referred to as creeping flow, and we have got a very simple form which Navier-Stokes equation takes in this case, mu times del square V plus rho times B minus gradient of P is equal to 0. There are various other simpler forms. The most important, for instance, I would like to refer to the ones where we have got buoyancy driven flows. In which case the density variations can be ignored everywhere except in the momentum equation by including a term which accounts for density variation. For this and various other cases, please refer to the following books. So, just for the sake of recap of what we have discussed so far in connection with our conservation laws, few good references could be the books by Batchelor, this book published in 1973 is one of the classic books, Introduction to Fluid Dynamics. By Cambridge University Press. A more recent book is that by Kundu and Cohen. Its most recent edition was published in 2008 by Academic Press. The book is simply titled as Fluid Mechanics. It's published by Academic Press. So, these two references will give fairly detailed derivation of the governing equations of fluid flow which we had discussed so far. I would just like to mention few other simplified cases that we have already seen: incompressible flow, which leads to simpler continuity and momentum equations. We have already seen inviscid flows, which is or approximations, very useful approximations for the case of high speed aerodynamics, and these are given by Euler's equation. We can also have yet another possibility, that if you are dealing with high speed flows away from the solid surfaces, where we can ignore not just the viscosity, that is to say our fluid is or flow is inviscid, if in addition it is also what we call irrotational, that is the vorticity present is very small or negligible, we can represent our velocity as a gradient of a scalar function which is called velocity potential, and in that case we have got a further simplification, that instead of solving 4 equations, one for continuity and 3 momentum equations, we can have a single equation, single scalar equation which is called Laplace equation for a scalar velocity potential. So, numerical simulation in this case becomes a lot easier. We need to just solve for the scalar velocity potential, take its gradients, and we would get all the velocity components. we can invoke Bernoulli's equation to get the pressure field and so on. So, this simplified potential flow model is also very commonly used in some hydrodynamic flow simulations as well as in aerodynamic flows. In the next lecture we will cover or discuss in detail the energy equation. We would start from the first law of thermodynamics and we would obtain integral form of energy equation, which is, just for the sake of summary, we have given here del by del T of Cv rho eta d omega plus surface integral of rho eta v dot dA is equal to q into d omega, this is a volume integral, minus q dot dA plus v dot tau dot dA. On the left hand side is eta, that this represents the total energy per unit mass of a fluid, which consists of internal energy as well as kinetic energy. The potential energy has been incorporated in this flow work on the right hand side. So, the first term is temporal variation, the second one is convection of eta with velocity field. The first term on the right hand side represents volumetric heat generation due to volume sources in the fluid medium. The second term q dot dA, q are surface fluxes, so that represents what we call heat diffusion through the control surfaces, and the last term represents the flow work, which involves the work which the fluid must do against the stresses which incorporate the effect of both surface forces as well as body forces. Now, how do we obtain this equation starting from the first law of thermodynamics? That is what we will discuss in detail in the next class, and we would obtain this integral form as well as appropriate differential forms for the energy equation.